Transformers play a critical role in the efficient and reliable distribution of electrical power in modern society. They are fundamental components of power distribution and transmission networks, facilitating the transfer of electrical energy between different voltage levels. Through electromagnetic induction, transformers enable voltage transformation, power loss reduction, electrical isolation, voltage regulation, and system flexibility. With their ability to step up or step down voltage levels while keeping the frequency unchanged, transformers form the backbone of our electrical infrastructure, ensuring the safe and effective use of electricity in our daily life. Otherwise, the electrical current flowing in the coils and the magnetic field alternating in the core produces transformer losses. The losses associated with the coils are called the load losses, while the losses produced in the core are called no-load losses. This video aims to provide a comprehensive overview of transformer losses, their impact on efficiency, and methods to minimize them. What are load losses in transformer? Load losses, also known as copper losses, refer to the power losses that occur in a transformer's windings or coils when electrical current flows through them. Load losses vary according to the loading on the transformer. They include heat losses and eddy currents in the primary and secondary conductors of the transformer. These losses are primarily caused by the resistance of the copper conductors used in the transformer. When electric current passes through the windings, it encounters resistance in the copper wire, which leads to power dissipation in the form of heat. This dissipation occurs due to the Joule effect, where energy is converted into heat as a result of the resistance of the conductor. Load losses are proportional to the square of the current, I superscript 2, flowing through the windings and the resistance, R, of the conductor, according to Ohm's law. Load losses are directly related to the amount of electrical power being transferred or consumed by the load connected to the transformer. They are named as load losses because they occur when the transformer is under load, i.e., when it is supplying electrical energy to connected devices or equipment. These losses are an inherent characteristic of transformers and represent a conversion of electrical energy into heat, which is dissipated into the surrounding environment. Minimizing load losses is essential to improve the efficiency of transformers and reduce energy waste. Transformer manufacturers strive to design and construct transformers with low-resistance windings and high-quality conductive materials to minimize load losses and enhance overall efficiency. Load losses are an important consideration in transformer design and operation, as they impact the overall efficiency, temperature rise, and power rating of the transformer. By minimizing load losses, the efficiency of power transmission and distribution systems can be improved, leading to energy savings and reduced operational costs. Now let's talk about no-load losses. What are no-load losses in transformer? No-load losses, also known as core losses or iron losses, are an important aspect of transformer operation. They refer to the power losses that occur in a transformer's magnetic core when it is energized without any load connected to its secondary winding. These losses are independent of the load current and primarily arise from the operation of the core itself. No-load losses do not vary according to the loading on the transformer. They are constant and occur 24 hours a day, 365 days a year, regardless of the load, hence the term no-load losses. They can be categorized into 5 components. 1. Hysteresis losses in core laminations. Hysteresis losses occur due to the magnetic properties of the core material. When the magnetic field within the core alternates, the core material undergoes cyclic magnetization and demagnetization. This cyclic process results in energy dissipation as heat, known as hysteresis losses, as the core material resists the changes in magnetization. 2. Eddy current losses in core laminations. Eddy current losses occur due to the presence of circulating currents induced within the core laminations. These circulating currents are caused by the changing magnetic field and encounter resistance in the core material, leading to power dissipation in the form of heat. Thinner lamination of the core steel is often employed to reduce eddy current losses by minimizing the area available for circulating currents to flow. 3. Square of the current, I superscript 2. Multiply resistance, R. Ohm's law losses due to no-load current. These losses result from the resistance of the windings and the current flowing through them, even when the transformer is operating without a load. However, these losses typically contribute a small portion to the overall no-load losses and are often neglected. 4. Stray eddy current losses. Stray eddy current losses occur in core clamps, bolts, and other core components. These losses arise from the presence of circulating currents induced in these components due to the changing magnetic field. While they are present, stray eddy current losses are usually minimal compared to hysteresis and eddy current losses in the core laminations. 5. Dielectric losses. Dielectric losses occur in the insulation materials used in the transformer. These losses are associated with the electric field within the insulation and result in a small portion of the overall no-load losses. The biggest contributor to no-load losses is hysteresis losses. Hysteresis losses come from the molecules in the core laminations resisting being magnetized and demagnetized by the alternating magnetic field. This resistance by the molecules causes friction that results in heat. The Greek word, hysteresis, means to lag and refers to the fact that the magnetic flux lags behind the magnetic force. Choice of size and type of core material reduces hysteresis losses. What are the impacts on the transmission and distribution networks of transformer losses? Transformer losses have significant impacts on the efficiency, reliability, and cost-effectiveness of transmission and distribution networks. These losses occur in both the core and windings of the transformer and can result in various consequences throughout the electrical system. One of the primary impacts of transformer losses is reduced efficiency. Transformers are not 100% efficient, and a portion of the energy passing through them is lost as heat. These losses include load losses, caused by the resistance of the windings, and no-load losses, which consist of core losses, such as hysteresis and eddy current losses. The overall efficiency of the transformer is reduced when losses are high, leading to higher energy consumption and increased operating costs. Additionally, transformer losses contribute to voltage drops within the transmission and distribution network. Load losses, which occur when current passes through the windings, result in voltage drops proportional to the load. These voltage drops can impact the quality and reliability of the power supply, affecting the performance of electrical devices and potentially causing disruptions in sensitive equipment or processes. Power quality is another aspect affected by transformer losses. Core losses introduce harmonics into the system, resulting in poor power quality. Harmonic distortions can cause voltage fluctuations, increased heating in equipment, and interference with sensitive electronic devices. These power quality issues can lead to operational problems, reduced equipment lifespan, and increased maintenance requirements. Transformer losses also contribute to increased system loading. As losses generate heat, the temperature of the transformer rises. Higher temperatures can reduce the transformer's capacity to handle load variations and can lead to premature aging or failure of the equipment. This increased loading requires careful monitoring and management to avoid overloading and ensure operational safety. Energy losses due to transformer losses represent wastage within the transmission and distribution network. These losses can be substantial, especially in older or less efficient transformers, leading to increased fuel consumption and higher greenhouse gas emissions. Minimizing transformer losses is crucial for promoting a more sustainable and environmentally friendly electrical grid. The sizing and cost considerations of transformers are also impacted by losses. Higher losses necessitate larger transformers to compensate for the losses and maintain proper voltage regulation. This results in additional capital investments, increased equipment sizes, and higher maintenance costs. Optimizing transformer losses can lead to cost savings and improved overall system efficiency. How to reduce transformer losses? Reducing transformer losses is a crucial aspect of maximizing energy efficiency and minimizing wastage in electrical systems. Transformers are essential components in power transmission and distribution networks, and their losses can have a significant impact on overall system efficiency. By implementing various strategies and technologies, it is possible to reduce losses and improve the performance of transformers. One of the primary types of losses in transformers is load losses, also known as copper losses. These losses occur in the windings of the transformer due to the resistance of the conductive materials used. To minimize copper losses, it is important to select transformers with optimized winding designs and low-resistance materials, such as high-conductivity copper or aluminum. Additionally, optimizing the winding configuration and reducing the length of the conductors can further minimize resistance and subsequent copper losses. No-load losses, or core losses, are another significant component of transformer losses. These losses occur in the core of the transformer and are independent of the load. Core losses consist of hysteresis losses and eddy current losses. Hysteresis losses are caused by the magnetization and demagnetization of the core material as the magnetic field alternates. Eddy current losses result from the circulating currents induced in the core material. To reduce core losses, it is vital to use high-quality core materials with low hysteresis and eddy current losses. Employing thinner laminations in the core construction reduces the area available for circulating currents, thus minimizing eddy current losses. Proper core stacking and clamping techniques can also help reduce stray eddy current losses. Efficient cooling systems play a crucial role in reducing losses and maintaining optimal operating temperatures. Heat generated by losses in transformers can impact their efficiency and lifespan. Implementing effective cooling methods, such as fans, radiators, or oil cooling, helps dissipate heat efficiently, keeping the transformer within the appropriate temperature range and improving overall efficiency. Regular maintenance and monitoring are essential for ensuring optimal transformer performance and efficiency. This includes keeping the windings clean, inspecting for loose connections or damaged insulation, and performing oil analysis to monitor the condition of the insulating oil. Adequate monitoring of transformer parameters, such as temperature, load, and voltage, can help identify any issues affecting efficiency and enable timely corrective actions. In addition to specific transformer-related measures, implementing energy-efficient practices in the overall power system can indirectly contribute to reducing transformer losses. These practices include voltage regulation to maintain stable voltage levels, power factor correction to minimize reactive power losses, load management to balance the load across transformers, and minimizing harmonic distortions that can cause additional losses. Overall, reducing transformer losses requires a combination of careful design, material selection, maintenance practices, and efficient operation. By implementing these strategies, it is possible to enhance transformer efficiency, minimize energy waste, and contribute to a more sustainable and reliable electrical power system.